Okay. Good evening. We have micro operations, arithmetic micro operations, a logic micro operations, logic micro operations. What is a logic? Arithmetic micro means what? Performing the arithmetic operations like addition, subtraction, division, multiplication, increment, and so on the registered bits on the data which is registered. Right, comes to the logic micro, the logic specifies the byte for one of the bits stored in the registers. Right, that is the difference between logic and arithmetic micro operation. In these logic micro operations, these operations consider each bit of the register separately and the bits are treated as a binary variable. Each bit of the register is treated as a binary variable. Let us consider we have two registers R1 and R2. If you want to perform an exclusive micro operation, this is the symbol used for exclusive OR of R1 and R2. You already know how to perform this. In binary adder subtractor, I explained about the exclusive OR gates. Exclusive OR gates. మర్చిపోయా అవునా Is my voice is clear? Is my voice is clear? Yes. In today's session, we'll start about the logic micro operation. Micro operation stored in the registers. We'll call it as a micro operations. Right? Different micro operations we have like register transfer operations, logic operations, shift operation, and arithmetic operations. In our previous session, we discussed about the arithmetic micro operation. Now, in class, we'll see operation. The logic micro operations are the binary operations for the string of bits stored in the register. They are the operations for the string of the bits in the register. So, in these operations, each bit of the register is treated as a binary variable. Consider an example. You have two registers R1 and R2. Two registers R1 and R2. Right? When I want to perform the exclusive OR operation between these two registers, here you observe, did you observe this register transfer language? So I have written this as P colon. I have written this as P colon R1 exclusive OR. Right? So what do you mean by this P? I explained what is this P. This P is a control variable which isn't in the or is in your form a Yes. Yeah, okay. Let us start logic micro operations. The logic micro operations are the micro operations which are performed on the string of the bits stored in the registers. Right? So these operations considers each just as separately, and those bits are treated as a variable. Right? Logic micro operations, the operation for string of the letter the example if to one exclusive with of R2, R1 exclusive or with R2. Just observe the register transfer language. Just observe the register transfer language that I have written here. P colon R1 tends to R1 exclusive or with R2. In the pre-outer, I explained what is this P. P is a control wave which comes from the control unit. Where is control unit present? This control unit is present inside the ALU. ALU is having mainly three components. Sorry, your CPU mainly having three components: ALU, control unit, and different computer registers. Whenever you want to transfer the content of the register, then control unit will send the signals. So using this control variable, whenever the value of this P is equal to 1, then the transfer will occur. Now see here, and I explained exclusive or operation also. At the time of binary adder subtractor, we have used this XOR gate we have used. What is the truth OR gate? When you XOR a bit with this, that bit itself. When you XOR a bit with 1, the out complement. See here. When you are XORing the register R1, these are the contents of the register R2. When you XOR this register, when you XOR the bit 0 with 0, what is the output? Here I am XORing with 0, so the result is itself. 0 will be your result. When it comes to here, when you are XORing the bit with 1, the output should be the complement. What is the complement of 0? It is 1. So the result is 1. When you XOR any bit with 0, the result is itself. So it is 1. When you XOR any value with 1, the result is its complement. What is the complement of 1? It is 0. Right? Now, we have 16 logic micro operations. There are 16 logic micro operations that you can perform. Those are like this. So this is the corresponding Boolean function, how to represent with Boolean function, and how to write a micro operation that we have mentioned here. And here we have mentioned the name of that particular logic micro operation. These are all the logic micro operations: and, or, nor, XOR, complement, NAND, so on. Those are all known as the logic micro operations. Right? First micro operation is clear micro operation. Clear logic micro operation. What this micro operation will do? This will clear the content of the register. That means everything in the register will become 0. Everything will be cleared. That is your clear micro operation. And the next one is, if the micro operation is A and B, this is the symbol used for AND. This is used for AND. What do you mean by AND micro operations are true? Or in other words, we can say when both the bits are 1 and 1, in that case the result will be 1. In all other cases the result will be 0. That means 1 and 1 will give you 1, 1 and 0 will give you 0, 0 and 1 will give 0, 0 and 0 will give you 0. And means both should become true. Both should be equal to 1 and 1. Next micro operation is like A and B complement. What is B complement? If B equal to 1, the complement will be 0. If B equal to 0, the complement will be 1. The next operation is F tends to A. That means content of the register A will be transferred into the register. Content of A will be completely transferred. Next micro operation is A complement and B. Next is B. Like this, we have different logic micro operation. We have 16 logic micro operation. You know how to perform this exclusive OR operation. What is this OR operation? And means what? Both should be true. Both should be equal to 1. In case of OR operation, any one value should be equal to true, then it will be 0. Sorry, it will be true. For example, if the bits are 1 and 1, both are true, so the result is true, that is equal to 1. If it is 1 and 0, at least one value should be true, or at least one value should be equal to 1, so the result is 1. For 0 and 1 also the result is 1. For 0 and 0 the result is 0, because at least one value should be equal to 1 or 1 should be true. In case of 0 and 0, both are false, so the result is 0. NOR is just the complement of the OR operation. Next, exclusive NOR operation, complement, NAND. Here in the first micro operation, we have clear micro operation, means we have cleared the complete content of the register. Everything we made as 0. When it comes to the last one, we will set all the bits in the register to 1. These are the different logic micro operations that you can perform on the register content. Right? Now see the hardware implementation of this logic micro operation. I already told you that different 16 micro operations we have, but we can implement them using the basic gates, basic operations like AND, OR, XOR and NOT. NOT is also known as the complement. Okay? These are the 4 basic gates used to get all the 16 desired logic micro operations. Let us see the hardware implementation. I are going to use a multiplexer MU, which is of size 4 by 1, because here we are taking 4 gates, 4 basic gates we are considering. So in those 4 basic gates, those are OR gate, this is your OR gate, this is your XOR gate, and this is your NOT gate. These are the 4 basic gates we'll be using to get the 16 micro operation. Right? So the 0th input line of the multiplexer is connected with the output of the AND gate. First input line is connected with the output of OR gate. Second is connected with output of XOR gate with output of the NOT gate. Just so when you are using a multiplexer of size 4 by 1, so how many selection lines should be? Your selection line should be equal to 2. Based on this selection line value, any one input line will be your output of the when values are 0 and 0. The corresponding decimal value for 0, 0 is 0. Whatever is connected to the 0th input line of the multiplexer will be your output. Right? So here to the 0th input line, you are connected the output of the AND gate. So the output will be an AND operation. In the same way, If the value of the selection lines are 0 and 1, the corresponding decimal value is 1. So to the first line of the multiplexer of the OR gate, so the micro operation performed is OR. Similarly, when it is 1 0, the value is 2. Whatever is connected to the second input line, that will be your output, that is your XOR gate. In the same way, to the third line, we have connected the NOT gate. Therefore, if the selection line values are 1 and 1, hello. If the selection line values are 1 and 1, the corresponding decimal value is 3. So whatever is connected to the third input line, okay. ఒక్క నిమిషం. ఓకే, మళ్ళీ ఎట్లా పోయింది వచ్చింది. నేను కంటిన్యూ చేయను. Whenever the input selection line values are 1 and 0, the corresponding is third line of the multiplexer NOT gate is connected. So the logic micro operation performed is a complement or a NOT operation. Right? So when you see the hardware implementation, here 4 by 1. And what are the inputs of the multiplexer? I already explained. The inputs of the gates and OR, XOR and NOT gate. Now we will see the applications of the operation. Let us see what is this selective set. In selective set operation, the bits in the register A are set to 1 when the corresponding bits in the register B are equal to 1. Listen carefully. When the bits in the register B are equal to 1, then the corresponding bits in the register A are equal to 1. Let us see the example. Here, this is your A register which contains the data bits 1010. And this is your register B which contains the bits 1100. What is selective set? The registered bits of A are set to 1 when the corresponding bit in B is equal to 1. Let us see. Here the bit in A is 0. Let us see whether it is 0 or 1. What is the corresponding bit in B? The bit in B is 0. Therefore, the content of A will not be changed. It will be 0 only. Similarly, here the bit in B is 0. So, the content of A won't be changed. It will be 1 only. Now see here, the bit in B is equal to 1. According to the definition, whenever the bit in B is equal to 1, the corresponding bit in A should be equal to 1. Right? So this value is going to be modified. In the same way, the fourth bit in register B is equal to 1. Whenever the value of B equal to 1, current A should also be equal to 1. If it contains 0 or whatever may be the data in A, If the corresponding B is equal to 1, then the value in A should be equal to 1. Right? So these are the two values that needs to be changed. When you observe this, here I have considered 4 combinations: 0, 0, 0, 1, 1, 0 and 1, 1. 4 different combinations I have considered. See, when you see the truth table 0, 0, after performing this selective set operation between A and B, what is the result you got? 0, 0 will gives you 0, 1, 0 gave you 1, 0, 1 gave you 1, 1, 1 gave you 1. What is this? 0, 0. When both are false, you are getting this false as result. When 1, 0 means when at least 1 is true, you are getting it as true. Next, 0, 1. At least one value is true, the result is true. Here, both are true, therefore the result is true. That means it is equivalent to the OR micro operation. Therefore, we can say that selective set operation is equivalent to the OR micro operation. Right? Is it clear? First of my application, selective complement micro operation. Selective complement. In case of selective set micro operation, whenever the bit value in B is equal to 1, then the corresponding bit value of A should also be equal to 1. But in case of selective complement micro operation, whenever the bit value of B is equal to 1, whenever the bit value of B is equal to 1, then corresponding bit in A should be complemented. Corresponding should be complemented. Consider the same example. These are the bits of A. These are the bits of B. Whenever the bit value of B is equal to 1, corresponding bit of A should be complemented. Right? Here, the bit value of B is equal to 0. Therefore, there should not be any change in A. It will be 0 only. When the bit in B is 0, the corresponding A bit should not be changed. It should be 1 only. Now see here, the bit value of B is equal to 1. Whenever it is 1, corresponding bit in A should be complemented. Selective complement. Select the bit in B with the value of 1. Corresponding should be complemented. Select the value in B and the corresponding value in A should be complemented. That is what selective complement operation is. So here it is 1. The corresponding bit in A is what? It is 0. So the result should be the complement of 0, that is 1. In the same way, the value in bit is 1. Then the corresponding value in A should be complemented. It is 1. The complement of 1 is equal to 0. Now let us see this 0, 0. What it is giving? It is giving you 0. When you perform 1 with 0, you are getting 1. And when you are performing 0 with 1, you are getting the same value 1. When you are performing selective complement with 1 and 1, you are getting the 0. When you see this truth table is just similar to your XOR truth table. Exclusive OR, we'll also call it as XOR truth table. When you XOR a value with 0, we'll get the same value. When you XOR any value with 1, you are getting the complemented value. When you are XORing with 0, you are getting the same value 1. When you are XORing with 1, you are getting the complemented value. That is complement of 1 you are getting as 0. Therefore, we can say that selective complement is similar to your XOR gate. Whereas selective set operation is similar to your OR gate or micro operation. The third operation. In this selective clear operation, the bits in A are set to when the corresponding bits in the register B are 1. That means if B equal to 1, then corresponding A should be equal to 0. See here. See here. When B is equal to 0, there will be any J. When B is change in A, it will be 1 as it is. Now, when there is a 1, then corresponding value in A, whatever the data is present in A, you should make it as 0. You should clear that value in A when B equal to 1. So, the third bit of B equal to 1. Therefore, the third bit of A should be equal to 0. Similarly, bit of B is equal to 1. Irrespective of the data present in A, you should make it as 0. So, when you see this truth table, this is just equivalent to A and B complement. A complement. So, selective clear micro operation is equivalent to A and B complement micro operation. Move on to the mask operation. So, mask operation is clear operation. But in case of selective clear operation, A bit 0 equal to 1. But in mask operation, the bit value is clear, the corresponding bit be 0. Actually, it was raining heavily here. That is the reason sometimes the voice is breaking. If you don't understand, I'll just revise at the end. So, mask operation is equivalent to the selective clear. But what happens in selective clear? A equal to 0 when B equal to 1. But in case of mask operation, A is equal to 0 when B is also equal to 0. The corresponding B is also equal to 0. See this example. Here, the value of B is 0. When B is 0, corresponding bit in A should be equal to 0. In the same way, second bit of B is 0. So, corresponding second bit in A should make it as 0. You should clear the corresponding bit in A. Next here, when the bit in B is equal to 1, there should not be any change in A. It will be 0 as it is. When the bit of B equal to 1, there should not be any change. It will be 1 as it is in A. You just see the truth table. 0, 0, it is giving you 0. 1, 0, it is giving you 0. 0, 1, it is giving you 0. 1, 1, it is giving you 1. That means the result is 1 only when both the values are 1. It is just equivalent to your AND micro operation. Therefore, mask operation is indirectly equivalent to AND micro operation. Where in AND micro operation, when both the values are 1, then only the result will be 1. In all other cases, if at least one value is 0, the result will be 0 only. And the last one is insert micro operation. Insert micro operation. In this insert operation, it is you put a new data into the content of the register. If your let us suppose A is a register which already having some data, something like 100. If group of bits in A, if you want to replace them with this new value, in that case you can use this insert. Whenever you want to insert a new value into a group of bits, you can use this. Right? So to perform this insert micro operation, you can done in two stages. First, you need to perform the masking. Masking is what? Masking is indirectly equivalent to your AND micro operation. In the second step, you need to perform the OR operation with the required bits. Mean whatever the data you want to change or whatever the data you want to insert, with the data we need to perform OR operation, right? So first perform AND operation, that is first perform masking, and then perform insert the new data, that is perform ORing. Let us see the example. I want to insert a new data 1001 in place of 011 in the register A, which contains the data like this. This is the data of your A, 0110 1010. What I want to do in this, the group of bits, some group of bits of A needs to be replaced. 011 I want to replace with what data? 1001. Let us see how to perform this. What is the first step? First, you need to perform masking. Now, let us see how to perform this masking. Whenever you want to perform masking, place all zeros wherever you want to replace, and the rest of the values will be equal to 1. This is your A, right? What it contains? 0110 1010. This is your A. This is to be masked with this data. What is this? Excuse me. This is what? How to perform this masking? These are the group of bits I want to replace. Right? Wherever you want to replace, there you just put zeros. So, in place of these 4 bits, you place 4 zeros. Rest of the values will be 1. N number of values you may have. Rest of the values should be equal to 1. This is masking. Now, you need to perform the AND operation. With this data, you need to perform masking. You know how to perform AND operation. If at least one value is 0, then the result will be 0. 0, 1 will give you 0. 1, 1 gives 1. 0, 1 gives 0. 1, 1 gives 1. 0, 0, 0. 0. All the rest will be 0 because here we have zeros. Right? This is the first step. What is the first step? First, I need to perform masking. How to perform this masking? Wherever you want to replace, there you should have 0. You just place 0. Remaining all will be 1, and then perform AND operation. This is your first step. What is a perform OR operation with the group of bits which you want to replace? What is to be replaced? I want to replace 0110 with 1001. Right? So, I want to replace the bits 1001. What is the output of this first step? 4 zeros followed by 1010. The first step output of your first step. Now, how to perform the OR operation? How to perform the second step? Perform OR with what? With the group of bits which you want to replace. What is to be replaced? I want to replace a 1001. Just observe here. 1001 I want to replace. So, it will be 1001. Rest of the values will be zeros only. Rest of the values will be zeros. With these two, A and B, now you perform OR operation. What you will get? 0 or 0 will be 0. If at least one value is 1, then the result will be 1. That is your OR operation, right? So 10 is 1. 00 is 0. 101. And so So when you see this, what is the result you got? 1, 1, 1, 0, 1, 0. What is the original data given? What is the original value of A? Original value of A is 0, 1, 1, 0, 1, 0, 1, 0. What is my question? I want to insert 1, 0, 1, 0, 0, 1 where in place of 0, 1, 1, 0. Let us see whether you got the same or not. In place of 0, 1, 1, 0, I want to replace 1, 0, 0, 1. You got the required value, right? So this is performing insert operation. Let me explain this again. In case of insert micro operation, this is used whenever a new data into the registered value. How to do this? In 2 steps you can perform this. First step is perform masking. Second step is perform ORing. Perform OR operation. How to perform mask operation? Example, this is the given data, and in this data, this group of bits I want to replace with 1, 0, 0, 1. Right? So whenever you want to perform masking, wherever you want to replace, I want to replace these bits. There you just put zeros and remaining all will be 1. Right? Now you can perform AND operation between A and B. You know how to perform AND operation. That is the first step. This is the output of your first step. Now the second step is perform OR operation. With what data? With one is output of the first step. That is this first step output. Next, with the group of bits which you want to replace. I want to replace with what data? I want to replace with 1, 0, 0, 1. Rest of the values will be zeros. Next, perform OR operation, which will give you your required result. Right? These are the applications of your logic micro operation. This is very, very important, applications of logic micro operation. First one is, I am just revising, just listen carefully. First one is selective set operation. In selective set operation, what happens? A will be equal to 1 when corresponding B is 1. In simple terms, I can find only if B equal to 1. Right? Similar. So this is equivalent to OR micro operation. Next, selective complement operation is A equal to A bar if and only if equal to A bar if and only if B equal to 1. Third one is clear. What? A equal to 0 if and equal to A is if B is 1. Next, mask operation is just similar to selective clear operation only. So what happens here? A equal to 0 when B equal to 0. A equal to 0 when B is equal to 0. This is just equivalent to your AND micro operation. And the last one is insert micro operation. So this you can done using 2 steps. First one is perform masking. Second one is perform ORing. So this is about your logic micros. Is it clear for everyone? Shall we start the quiz or shall I proceed with the next topic? That is shift micro operations. If you have any doubts, just let me know, ma. If you have any doubts, let me know. Okay, quiz. Okay. Okay, I'll start the quiz. Before that, let me know if you didn't understand any of these logic micro operation. I'll try to explain it again. After that, we'll start the quiz. We'll give 5 minutes for doubts. After that, I'll start the quiz. Okay, you want me to repeat the first micro operation? This is not the first micro operation. Yeah, okay. This one selective set. Someone asked me to repeat the first micro operation. I think this is the applications, right? Okay, first application of your logic micro operation is selective set operation. In selective set operation, A equal, listen carefully. In simple terms, I am telling you here that I didn't write here. A equal to 1 if and only if B equal to 1. A is 1 if B is 1. See, what is the value of B? 0. No, so there will be no change in A. It will be 0 only. What is the value of B? 0. So there will be no change in A. This will be 1 only. Next, 2 should also be equal to 1. That is what the definition. A equal to 1 if and only if B equal to 1. So, whenever your B is equal to 1, your A should also be equal to 1. Similarly, here also, your B equal to 1. So, your corresponding A should also be equal to 1. Truth table 0, 0, you are getting 0. 1, 0, you are getting 1. 0, 1, you are getting 1. 1, 1, you are getting 1. This is similar to your micro operation. At least if one value is 1, you are getting the output as 1. So this is just equal to your micro operation. Selective complement is A equal to A complement when B equal to 0. Sorry, when B equal to 1. B equal to 0, no change in A. B equal to 0, no change in A. Now B equal to 1, then A equal to A complement. 0 complement is 1. When B equal to 1, A should be equal to its complement. 1 complement is 0. When you see this truth table, it is equal to your XOR micro operation. And the third one is selective clear. Clear means equal to 0. Clear means 0. If B equal to 1, then A equal to 0. Whatever may be the value of A, it should be cleared. So see this example. B equal to 0, no change in A. B 0, no change. B 1, so A should be 0. B equal to 1, so A should be equal to 0. This is equal to your micro operation A and B complement. A and B complement. Last one is mask operation. Mask operation is A equal to 0 if B is 0. A equal to 0 if B is 0. So if B is 0, A should be 0. B is 0, A should be 0. If B is 1, there will be no change in A. A will be 1, 0 only. And the last one is insert micro operation. This can be done using masking followed by ORing. How to perform masking? This is the given register A. In this, wherever you want to replace, there you just put zeros. Remaining all will be 1. And perform AND operation. This is the first step. Next, in the second step, consider the output of your first step and perform ORing with the data. What is the data? What is the data you want to replace? That should be written here, and the rest of the values will be 0. So I want to replace with 1001. Rest of the values will be 0. And perform the OR operation. So when you observe this is the data replaced with the required value 1001. These are the applications of your logic micro operations. Any other doubts? Any other doubts? Okay, ma.